Hi everyone, I'm Brennan Ungul and this is my partner Oscar Sujana. Today we're going to do our presentation on networks and spanning trees. So first we're going to talk about a couple of mathematicians, namely Arthur Cayley, who presented a different way to look at trees. So if we can revise a bit on our Math 1D, and we have partial derivative of xy equals y, and what he says is that the partial derivative of x is an operator on xy. And if the operator is written to the right of the operand, such as xy delta x, this whole expression is known as an operandator. So xy delta x is essentially known as an operandator. And in our third bullet point, we do say QPU can be written as a summation of Q times PU and QPU. And in tree form, so that left side of the tree is Q times PU and the right side is QPU. And QP and U are each operandators. So we'll discuss this a bit further in our next slide, which talks about Heinz Prüfer, another mathematician who extends on Cayley's formula and attempts to prove the permutation of different trees using his own representation. So he assigns each tree with n vertices a symbol which consists of n minus 2 numbers or characters, where each tree corresponds to only one symbol and each symbol corresponds to one tree. So this is a new method of counting trees which he introduces by counting sequences of length n minus 2 taken from a set of n numbers or characters. So for our next slide, we'll talk about Murufka.
So moving on to our next mathematician, in order to understand his solutions to the problem of the minimum spanning tree, we must first understand the proximity problem that Borufka expresses in his own terminology. So I've made this graph here consisting of 3 points. A lies on 1, 0, B lies on 3, 0, and C lies on 4, 0. We can see that the point closest to A is B. However, the point closest to B is C. So it doesn't mean that if point A is closest to B, the point closest to B is A. It doesn't have to be like that, which Borufka actually explains further using his theory of how minimum spanning trees should be formed. So in figure, the first one here with 40 points in a two-dimensional plane, Borufka says to connect each point or vertex with the nearest neighbor. So if we connect each vertex with its nearest neighbor, you'll see something that resembles figure 2, or you will see figure 2, a bunch of disconnected graphs or trees, because as you can see, they contain no cycles. And if you keep repeating it for each graph, treating each graph or disconnected graph as a vertex, connecting them with its nearest neighbor, you'll get figure 3, which is down here. And if you do it again, you'll get figure 4, which is an entire spanning tree. Now, in order to find out if this is a minimum or not, let's explore what Borufka says. So given a matrix M of numbers R alpha beta, where alpha beta is 1, 2 to n, where n is more than or equal to 2, all positive and pairwise different with the exception of R alpha alpha equals 0 and R alpha beta equals R beta alpha. So why do we say that R alpha alpha equals 0 and R alpha beta equals R beta alpha? This is because the subscripts of R, which are the two vertices, represent two vertices in the two-dimensional plane. So for example, if we take alpha and alpha, R represents the distance between these two vertices. Distance as in literal metric distance. So it could be in units of meters, kilometers, or centimeters, because Borufka attempts to explain this problem using practical examples. So if we take the distance between vertex A, vertex alpha, and vertex alpha, it will result in 0. And if we take the distance between vertex alpha and beta, it will be the same as the distance between vertex B and alpha. So now that we got this down, let's explore Borufka's solutions to the minimum spanning tree. The first step involves a set of n vertices in the xy plane, as we've seen before in the figure before this. So for example, there's vertex 1 to vertex n, where this notation with the square brackets with two vertices inside represents the distance between vertex I and j. Let's take j as an arbitrary vertex. We then connect vi to another vertex vm, where the distance between vi and vm is the minimum distance between vertex I and any other vertex in the two-dimensional plane, where in this case vm is the closest neighbor to vi. This will result in a graph which will be denoted by g. If G is not a fully connected graph, G can be expressed as a union of connected components, much like the disconnected graphs in figure 2, which we've seen before. So now let's consider alpha equals 11, which contains points 23 and 24. So if you see the previous figure, 23, 24, which is graph 11, and graph 12, 21, and 22. According to Borufka, In square bracket notation, K11, 12 and K12, 11 denotes the smallest distance between any 2 points in the disconnected graphs 11 and 12. So if you look at the submatrix here, which is part of a larger matrix, M, we can see that the smallest distance exists between vertex 21 and vertex 23, which we can gain through an edge and measuring the edge. Hence, if the points and disconnected segments or graphs are repeatedly connected to its nearest neighbor, Borovka writes that this is a solution to the given problem of minimum spanning trees, because as you can see, he does form a spanning tree at the end by connecting every point to its nearest neighbor. Now let's move on to the applications and problems that you can use with minimum spanning trees and networks. Today, there are amazingly dozens of uses for minimum spanning trees and networks. Most notably, minimum spanning trees are used in designing various types of networks, from phone lines, computer networks, electrical grids, and even GPS systems. Consider softwares like Google Maps. Every intersection or every connection in the road is a vertex, and each stretch of road is an edge. So you can really say how minimum spanning trees are used to find the cheapest or shortest routes for wires, cables, and roads. Another application of spanning trees exists in the approximation algorithms for NP-hard problems like the traveling salesperson problem. Currently, there are also many modern problems related to trees. An example of this is the arborescence problem. So far, we've explored only undirected graphs, but what about directed graphs? Directed graph, a minimum spanning tree of a directed graph is defined by Weisstein in Wolfram as if from a given node x known as the root vertex, there is exactly one elementary path from x to every other node y. This problem, or the arborescence problem, can be solved using the Chu-Liu-Edmonds algorithm, unlike the undirected graph where it can be solved using Prim or Kruskal's algorithm. Thank you for listening to our presentation. This is the works cited page.